Hi, in this video I'm going to talk about the CP violation and in neutral Kaon particles. First of all, let's look at the let's look at the CP violation in the mixing or CP violation in the wave function. So in neutral Kaons, we have actually we have actually two Kaons, one with a shorter lifetime and one with a longer lifetime. And this right here, wait a minute. Yeah, this right here is the K long with the longer lifetime, and the lifetime is around exponent -7, and the K short's lifetime is around exponent -10. So yeah, relatively this is the longer lifetime, this is the one with the longer lifetime, and this is the physical K0L is the physical eigenstate or the weak eigenstate, and this is actually equal to 1 over 1 square root of 1 plus epsilon squared, modulus of epsilon squared times epsilons times k01 plus k02. Here you can see that there is a quantity epsilon. Epsilon actually is a very small number which actually tells the mixing of k01 in k02. So k0 long usually decays into 3 pions, but as they have observed experimentally that k0 long does not always decay into 3 pions. Sometimes, I mean very rarely, but yeah, it does decay into 2 pions. So this epsilon numbers tells us or signifies the amount of violation or the amount of k01 part in the K long or the K02, K02, K01 and K02 are basically CP eigenstates. K01 has an even CP with +1, and K02 has odd CP with -1. Anyway, epsilon is basically the measure or the amount of CP violation, and we can also say that indirect, because in Kaons we can measure the CP violation directly and indirectly. Anyway, let's for the moment we are going to see CP violation in the mixing. So we are going to we can either proceed with K0 long or K0 short. So I'm here proceeding with the K0 long. So K0 long can be written as I showed you earlier. I can write this like this, and then I can write this CP eigenstate, that is K01, as a superposition of K0 and K0 bar. So I'm going to write these K01 in terms of K0 and K0 bar. K0 and K0 bar are actually the strangeness eigenstates. So I have so yeah, moving on, I'm going to write the strangeness eigenstates in I mean the CP eigenstate in terms of strangeness eigenstates, and eventually I'm going to get E plus 1, and yeah, I want to emphasize on one point or stress on one point that K0 and K0 bar, these two states are orthogonal. So if you take the inner product of so these are orthogonal. Anyway, moving on, let's call this E plus 1 P and epsilon plus 1 P and epsilon minus 1 Q. So I can rewrite the k long as 1 over and this 2 comes from it is common so I can take this out, take it into this expression. So yeah, so eventually I get an expression which explains the CPU violation in the mixing. Now moving on, okay, as I have explained the reason why we call it K0 long or K0 short, it's due to their lifetime. Okay, now if we look at the decay of K mesons, especially about the K0 and K0 bar, so we can have hadronic decay, we can have semi-leptonic decay, or we can have a complete weak decay. So these are the examples. In the first example, K0 meson is decaying into the D quark here is a spectator, and this Feynman diagram, yeah, D quark is a spectator, and S decays into U bar, and U bar via a W, and then W decays into a U bar and D. So this is hadronic decay. Similarly, here I have a semi-leptonic decay, and this one right here is pure weak decay. So as I told you earlier that we can get the CPU violation in Kaons. We can measure the CPU violation in two ways: indirect CPU violation and direct CPU violation. First of all, let's look at the indirect CPU violation. So in CPU violation, the wave function is the in indirect CPU violation, the allowed decay for the K02, which is the CP eigenstate, is that it can decay into 3 pions, and K01 can decay into 2 pions. But experimentally, when we see that, we don't observe. I will also discuss about the Fitch and Tarly experiment, Cronin, Fitch and Tarly experiment, which actually proved the mixing, which actually proved the K02 decaying into 2 pions. So actually K02, the branching ratio for decaying of K02 into 2 pions is 10 to the minus 3, and it can also happen that K0 short or K01 can decay into 3 pions, and the branching ratio for that is exponent minus, I think, 10, I'm not sure but that branching ratio is really small. Okay, so if we want to measure the CPU violation in this case, indirect case, so we have to measure the orthogonality, and the fact that K0 short and K0 long, K0 short does decay into 3 pions, a very small amount, and similarly K0 long does decay into 2 pions, which are not allowed by the CP eigenstates. Anyway, if we don't have any CPU violation, then these states would be they will be orthogonal, so that will be 0. We will not have any CPU violation. But if there does have a CPU violation, then in that case the non-orthogonality will actually tell us the amount of CPU violation. Anyway, we take the bra of K0L and take the inner product with the ket of K0S, and here if in the first term I will need to take the conjugate, so epsilon with the conjugate of epsilon would be epsilon steric. So anyway, k long and k short are not CPI eigenstates, so they are not orthogonal, but k01 and k02, which are the CPI eigenstates, so they are orthogonal. So in that case, I mean, this is very easy calculation. If you take the inner product of k01 and k01, you will get 1. If you take the inner product of k01 with k02, you will get a 0. So in that way, by proceeding this, you will get this actually, yeah, and epsilon static plus epsilon over 1 plus epsilon squared modulus squared, and we can write epsilon static plus epsilon in terms of 2 into real part of epsilon, and this is actually the amount of CP violation that we get, and this is experimentally, this is around exponent -3 or 0.3%. Now let's move to the direct CP violation. So for direct CP violation, we need to look at these two semi-leptonic decays. So if the widths of these two decays are not equal, then we are violating CP directly. Anyway, I mean, how we actually have to measure the charge asymmetry in order to prove the CP violation in this semi-leptonic case, semi-leptonic violation in the weak decays. Anyway, in order to measure, I mean, from the experimental point of view, we eventually we would look for E plus or E minus, and we can, I mean, easily tell if we get, I mean, by this simple rule, delta Q is equal to delta S. Delta S here is the strangeness and delta Q is the charge. By looking at the charge of the decaying product, we can tell that if it is a K0 or K0 bar. So if it is a plus, it is a K0. If it is a minus, I mean, if it is an electron, we have a decay product of K0 bar, and if we have a positron, we have a decay product of the K0. Moving on, we will actually measure the charge asymmetry, and if this charge asymmetry is 0, we have no CP violation, and if this charge asymmetry is something, we will have actually the CP violation. And by calculating, by doing the calculations, the final results show that there is a charge asymmetry which tells the amount of CP violation in Kaons. Okay, we can also look for the direct CP violation measurement in hadronic channel, and for that we have to calculate the R ratio. R ratio is the decay of K long. I mean, we have to look at this ratio. Eta 00 is K long decaying into 2 pions or K short decaying into 2 pions, and eta plus plus tells us about the K long decaying into a plus pion and minus pion. Similarly, this one. So by measuring this R ratio, we can measure the CP violation, and epsilon prime here tells us the CP violate the direct the direct amount of CP violation, which is around exponent -6, which is very small. Anyway, now I'm going to move on to the experiment the first experiment they performed to get to get results of the CP violation. Anyway, in this experiment, which Cronin, Fish, Turley, and some other guys, they designed this experiment in order to calculate or measure the CP violation, or to put an upper bound to the decay of K0 long into 2 pions. Anyway, the experimental setup was like that. They used a 30 JeV proton beam which hit on a beryllium target and which then produced kaons of 1 gigaelectron volt. So initially there are the K short and the K long mesons, they are mixed together, but as we know that the K short has a very short lifetime, so when they eventually decay, and through a calorimeter finally we get a beam which is purely K long, and they use the tungsten material in order to avoid the regeneration. Okay, what is the regeneration of kaons? The regeneration of kaons is that if we send a pure K long beam onto a regenerator, a material, then after interacting with the regenerator we will get again the K short and K long parts of the kaons. So yeah, this is called the regeneration. But since the point or the objective of the experiment was to measure the decay of K long into 2 pions, so they needed a very precise K long beam, so they did everything to avoid the regeneration of K01 or yeah, K0s. They are I cannot say they are similar because K0 short is the physical or the mass or the weak eigenstate, and K01 is the CP eigenstate, and K01 is definite and K0 short is not definite. Anyway, they used a helium gas as a vacuum medium because they cannot produce perfect vacuum, but helium is kind of a good medium for an approximate vacuum medium. Anyway, they use the 2-arm detectors placed at 22 degrees apart. I will show you the diagram explicitly if I have that. Let me show you. Okay, so here is the diagram of their experimental design. So these are the 2 arms which consist of the spark chambers and magnets, scintillators and water Cherenkov detectors. So this is the experimental design. Anyway, moving on. Now the placement of the detectors and the experimental setup was intelligently designed just to measure the 2 pion decay. So if we have 2 pion decay, so we have momentum of one particle, momentum of the second particle, and their net momentum would be at 0 degrees, so theta of 0 would be 1. So if when they measure the if they get a signal, then it will be from the 2 pions. Otherwise, if they have if the decay is the 3 pions, which are actually in this case the fact that they are trying to measure the 2 pions, 3 pions decay, which is the most likely decay, will count as a background. So for K long decaying into 3 pions, let's say these are the momentums of 3 pions, so their net momentum would be something like this, and that will be the value for the cosine of theta for that will be greater than 1. Anyway, now I'm going to show you the chart, the results of this experiment. Okay, so they look for for different mass ranges. First they look for 484 to 494, then from 494 to 544, and then 504 to 514, and this is actually the distribution of this is actually the distribution of cosine of theta, and as you can see that this is very precise. Anyway, the point is that at exactly at 499 approximately 499 mega electron volt, they observe a peak, the peak here, and this peak is actually, if you look at here, at cosine of theta is equal to 1, as I showed you earlier. So this was only possible if there is a decay like this, and which is actually the 2 pion decay. So they get a peak around cosine of theta equals to 1, and this was the proof of the decay of k long into 2 pion. Okay, so moving on. Yeah, so this is actually the k0 and k0 bar. I have not discussed their oscillations, but we can also find an expression for the k0 and k0 bar oscillations if we define a wave function and let that wave function evolve with respect to time. And also the k01 regeneration, I have also not discussed that explicitly here. I only focused on the CP violation in the Kaon sector. Anyway, that's it. See you next time. Ciao, out.